Hi. Hello. Hi. I'm Ryan, and I'm going to talk about my project. It's really exciting that there's so many people here that are interested in Node. It's really kind of weird, actually. It really wasn't meant to be this way. It was just some project to do. But yeah, it's very exciting, and it's neat to be here. And thank you for inviting me out here, and it's cool. So I'm going to give a bit of introduction to Node, and I'm very, very sorry to the people who are a bit more involved with the project and might already know this stuff. And for them, it might be boring, but I think there's a lot of people here who maybe have heard about Node or haven't, or it just kind of want to know what it is, and I want to give those people the chance to look at it. And you know, hopefully, if you want to geek out with me, we can get together in a corner and talk about cool things that might be happening with Node, and you know, lots of ideas, scheming, but we'll do that later. Oh, thank you. Okay, so right. Very simply put, Node is a set of bindings to Google's V8 JavaScript thing. And it's a set of bindings to, not to make graphics, although possibly, but primarily for building network programs. I guess that sounds a bit boring, but it's kind of exciting. So the way I want to structure the talk is kind of go from concrete to more abstract towards, you know, a look at the future. So let's start with examples first. Like, just get the code out there up front. So Node bind. Okay, so Node is a program. It's a command line program. First of all, it doesn't run in your web browser. It doesn't. It's not a GUI. It's a command line thing. And so to get it, you need to go to the website and download it and compile it. Hopefully, it should work if you have kind of a normal computer. If you have, you know, OpenBSD, then, well, you're already asking for pain, right? So. Okay, so here's the first program. So what this program does is, hopefully, if you're at all familiar with browser JavaScript, you should be able to kind of intuitively tell yourself what this is doing. But what this does is it prints the word hello, then it prints the word world, and then it exits. Okay, so the set timeout function is just like in the browser. It has the first argument a callback, and the second argument is the number of milliseconds to wait. And this console.log is like in the, what's it called, Firebug? The debugging thing in the web browsers. And it's become a kind of common API, and so it's supported in WebKit and yeah. So console.log print something to the console, to the standard out. And so it prints hello first, because you go through the script and you hit line 4 and it prints hello. And then 2 seconds later, it executes the callback. So after it's printed world, there's nothing left for the program to do, and it exits. And Node has this kind of natural ability that it knows when it has stuff to do. If there's some callback, if there's some socket open, or there's a callback pending, then it keeps executing. But once all the things are complete, it exits. So there's no explicit, you know, exit this program. So what you would do is you'd actually put that code into a file called helloworld.js, and you would run it with the node command, just like you would with Ruby or Python. And so it would print hello, and then 2 seconds later, it would print world. Excellent. Very simple, right? But let's make it complicated. Let's do another little program where we're going to print hello over and over and over again. And then when you hit the SIGINT signal, when you hit Control-C on your keyboard, you're going to print bye. And then you're going to exit the process. So now we're going to use the set interval, also a browser command, which prints something every half second, prints hello. And then on line 5, we're doing this weird thing where we have this process object, and we're adding a listener to it for the SIGINT signal, the interrupt signal. And then we give it a callback to execute when the process receives that signal. And so when it receives that signal, it prints out bye, and then it exits. You have to explicitly exit the process because you've overridden the interrupt signal. Okay, so that's cool. You have access to signals in Unix, which is great. We're trying to build a way to interface with the operating system. Signals are part of the operating system. The process object is emitting this SIGINT. And this is very much like in the DOM, in the web browser, when you have a button and you give it a callback when somebody clicks on it, right? When somebody sends the SIGINT signal to you, then you get a callback. When somebody clicks the button, you get a callback. It's exactly the same thing. So yeah, this process object is special. It's a you can think of it as analogous to the window global variable in the web browser. In Node, you have the process global variable. Node is a single process, and this process global variable refers to that process. So you can get things like the PID and the execution path, and you can get the memory usage, some cool stuff. This attaching callbacks and emitting is pretty common. So process isn't the only object in Node that emits signals. It emits has these callbacks that you can listen to. Almost everything does. So for example, a TCP server would emit a connection event every time somebody connects to it. And maybe if you're uploading a movie, the HTTP upload object would emit a data event every time you receive a packet of information. So now let's look at the TCP server interface. So we're going to make a little TCP server that starts on port 8000, is listening on port 8000. When you connect to it, you're going to send a message to the person who connects. So imagine you just telnet to this server. It's going to reply with, hello, and then it's going to close the connection. So how would that look in Node, just as a simple example? So right, on line 1, we're doing this weird thing with require, which is loading a module, the net module. On line 3, we're creating this server object S. And on line 5, we're adding a listener to oh, this is wrong, huh? This should be S right here instead of net. So you add a listener to the server object, and you're listening for the connection event. And when you get a connection event, you get this callback with a parameter which is the socket of the person, the server-side socket of the person that's connected. And on line 7, it's telling it to end the connection with pushing this data to it. So push hello to the socket, and then close it. And on line 10, you actually bind to a port and start listening. So if you wanted to try that, you could put it into server.js and actually telnet to your local host on port 8000, and you would get hello. Okay. So you can do file I/O in Node as well, as one would hope. And it's non-blocking as well. So here's a small program that will run the stat POSIX call on EDC password. And it's just going to tell you the last time that file was modified. So here in line 1, you're loading a module, the FS module, which is where all the file system related utilities are. And you pull out the stat function from that. It just returns an object with a bunch of functions. We're only interested in the stat function, so we pull that out. And then we run it, first parameter, the file name. And it gives a callback when it's completed. And this might seem very strange at first, because you would think, well, why can't I just call this function and then afterwards print out the modified time? Why do I have to give it this callback? But it's for a good reason. And the reason is that this file exists on a hard drive. Maybe it's even like an NFS partition and this file exists, in a different country. But whether it's the disk or a different country doesn't really matter. It's certainly, well, it could be cached by the file system, but likely it's not actually in your memory. And it's likely that somewhere something has to spin some physical hardware. You have to actually send out some packets over a switch if it's an NFS thing. Stuff is happening. It's kind of, we don't really know what's going to happen, but this stat function could take an unknown amount of time. It doesn't happen just like that. It takes millions of clock cycles. And Node has a particular philosophy of never waiting for stuff to happen, which includes waiting for the disk to spin. And for us just writing simple scripts, like moving file from here to there, that stuff happens very quickly. But if you scale that out to a server where you have thousands of people connecting and the time scales are very, very small, that matters. You can't shut down a server and wait to move a file from, one directory to another or copy some data from here to there, even if it only takes half a second or, 1 millisecond. If you have many, many people connected to your server at once, that's going to matter. And so Node takes a very hard philosophy, which is that we simply will never wait for that. Right, you get 2 parameters to the callback. The first is an error object, which may be null. If there was an error, for example, the file was not found, then that error object would be an exception, and you could throw it, or you could examine it and handle the exception. The second object, the second parameter is the stats object, which has various properties about the file. And so in line 6, we just print out the M time, the last time it was modified. Okay, so now getting slightly more complicated. We'll do not just a TCP server, but an HTTP server, which every time you connect to this HTTP server, it returns hello world to you, just some text. So again, you load the HTTP module, line 1. And in line 3 through 8, you create a server. You give it a callback to be executed every time you get a request. And in line 8, you just kind of bind to port 8000. And in the HTTP server, you get 2 objects. You get a request object, which will have information about what's being requested, like the requested path, or if you're uploading data, you can get a stream from that. And you have the response object, which is used to respond, obviously. Right. So just go through this quickly. On line 4, you're writing the head of the response, so 200 OK, with a very small header with just the content type. And then line 6, you write hello. And then line 7, importantly, you need to end your response. This may seem very peculiar, why you would need to do this, why you would need to explicitly end your response, but it comes up. We will see. So if you wanted to try this out, you could put that file into that code into a file, httpserver.js, run it with the Node program, and use curl and hit that URL, hit this server, and you would get back hello world. Yeah, you may notice that the connection is keep alive by default, and chunked encoding by default. We'll return to that. Here's a more complicated HTTP server. What this one will do is say hello, and then 2 seconds later it will say world. It's going to stream the HTTP response to you. This is important. You don't just return your HTTP, you don't return a response all in one go, but this is a stream of data, which could be paused, could wait for other things to happen. In this case, we're waiting for a timeout, but a stream could wait for more data to arrive on some other socket. We're never pushing out data and forcing the server to wait. We're simply doing what comes, we're simply streaming. The line 3 and 6 are the same as in the previous one. In line 8 through 10, you set up this timeout, and then you end the response. The client who's attaching to this knows that when you've got the hello, the response is not complete. It continues waiting for the rest of the response. And once you send this response.end, that will notify the client that okay, this is the end of that response. You know, now you can make a new request or disconnect or whatever. So again, put that in a file, curl it, you'll get hello. 2 seconds later, you'll get world. You can stream responses. So the HTTP module in Node is really quite low level. It does not parse headers. It does not examine your cookies. It does not have sessions. It doesn't have caching. It actually has very, very little. It's only taking apart this stream of data coming at you from some client and saying, here is the request, and providing a simple API for you to send the response to it. So importantly, it's low level enough that it allows you to stream these responses, but also hang these requests. That is, you can make a request to a server, and the server can simply not respond. You make the request, and it says, I'm going to wait for that. You know, I'm going to wait 1 second, 2 seconds, and then when the server decides that it wants to respond, it can respond. And this is necessary for these so-called comment applications, which is chat applications, where what you want is the new data that you want the updates about what's happened on the chat. So you make a request. This is long polling. You make a request. There's no new data, so you don't want to keep hitting the server with a bunch of requests, right? Like, no, there's no data. No, there's no data. No, there's no data. Oh, here's some data. You don't want to keep spinning like this. In long polling, what you want to do is request, have the server just not respond until somebody else has typed something on the chat, and then allow it to come back. This is the mechanism that you need to make any sort of real-time game or chat program, or it's basically the foundation of the real-time web. Comment is going to become a lot easier in the next year or two with the WebSockets API. But at the moment, that's not a reality for web browsers, right? You can't do WebSockets in IE6. You can't do it in IE7. And you do need to support those sort of things. You will need to do long polling. So Node is primarily and firstly designed for this long polling case. And this is all kind of enabled by this HTTP parser that I wrote. And the HTTP parser is really good, if I can toot my own horn. So it parses both requests. You know, HTTP has two sides, right? You have requests and responses, and they're different message streams. But the parser does both of them. It doesn't buffer anything. And in fact, these streams, the parser data that is needed to parse these streams takes 28 bytes per stream. That's really not a lot of space, right? When you start talking about servers that handle thousands of connections at once, keeping very little memory per connection is important. Servers that are buffering the request or doing any sort of buffering, basically, are going to be using a lot of memory. And things like this HTTP parser enable Node to use very little memory per stream. So yeah, if you're interested, do check out this parser. I think it's pretty nice. Right, so back to the examples. So now, what about like executing commands outside of Node? You have this Node process, but you want to interface with the operating system, and part of interfacing with the operating system is starting new processes. So there's this module called child process, and it has a function called X. How do you pronounce that? X, exec. And what that does is it executes some command. It buffers the standard out and standard error from that command, and then returns it to you in a callback. So if you want to do ls/, this will buffer up all the data that comes back from ls, and it will return it to you in a callback. So this is the typical interface that you get with Ruby or Python or anything, right? Just executing subcommands. Of course, you get a callback because who knows how long ls is actually going to take to run. We don't know. We can't block on that, so we give it a callback to be completed. But of course, we don't want to buffer the output from just any process. I mean, there might be some processes. I mean, Unix has this great thing called pipes, right? I mean, you can pipe you can do streams of data through processes and back, and we need to enable that in some way. And so Node is very careful never to force you to buffer anything, like in the previous example where it buffered the standard out and standard error. And so there exists a lower level API to execute a child process. It's a bit more complicated for sure. But here's an example where the command is called spawn. It's in the same child process module. And you're just loading the module in line 1. In line 3, you actually start the child process. And here we're going to use the cat command, which I'm sure you're familiar with. You send data to it, and it sends it back to you, right? Whatever you send to it on its standard in, it will send on its standard out. And so what we're going to do is we're going to say, hello, cat, send this data to it. And then 2 seconds later, we're going to say, bye. And cat is going to reply with the same thing. It's going to echo the stuff back to us. OK, so on line 5, you write to cat's standard in. Right? Standard in is the stream of cat that's going to receive data, and you can write hello to it. And then 2 seconds later, on line 7, on line 8, you end that standard in stream. You close the standard in of cat with by. Cat has the property that when its standard in is closed, that it will exit. On line 11, what we're doing is listening for stuff coming back from cat on its standard out. Remember, it echoes everything. And when we get data on cat's standard out, we actually print it to our console. So we're sending data to cat. It's coming back, and we're sending it to our standard out. You don't have to buffer data. So one of the new features is to unify all these different streams. You have requests, you have responses, you have standard in, standard out, you have standard in and standard out from your subprocesses. You've got file streams. There's a lot of streams of data going around. You've got TCP sockets. And one of the common things that you want to do with these sort of streams is take it and move it somewhere else. This is basically what everybody is doing with everything. You take some data, you push it out to some other site. Now, of course, not everybody's just proxying data. You usually want to take that data and like put some HTML tags around it. Maybe you're querying a database and you're getting something back and you stick some stuff on it and then send it on its way. But basically, everything is proxying data in some form or another. Where I'm attempting to go with Node is making this sort of proxying of data, these streams, and munging data together, munging other stuff with it, more simple. And the first of the ways of making this simple is the sys.pump command, which very simply takes data from one incoming stream and pushes it to an outgoing stream. And so we can do the cat example again. Everything's the same except line 12. Instead of listening on the cat.standardout and manually pumping it, manually pushing it to our standard out, we can simply have this command that abstractly does that. So you can pump. Okay, so what is Node? It's JavaScript outside the browser. And you can interact with the operating system in a kind of browser-like way, in that you get callbacks when things happen. And it has kind of a fancy HTTP library. But there's a bit more to this story. So first a benchmark. And certainly contrived and not real world, but it makes a small point. So what we'll do is set up a bunch of web servers, and from each of them we will get 1,000 people at once to connect to it and pull down a 1 megabyte file. And we just want to see how fast these web servers can serve this 1 megabyte file when 100 people at once are requesting it. And so I did this with Node and Mongrel, which is written in Ruby, and Thin, which is written on top of Event Machine, also Ruby, and Nginx, which is written in C, high-performance web server like Apache. And very surprisingly, Node does this very well. It's actually serving this file faster than Nginx is. This is the code. I won't go through it, but you can take this code and test it for yourself. See if you get the same thing. Importantly, Node is not serving a string here; it's serving a buffer. So there's some raw memory involved. But the action of going through this web server, every time somebody connects, it executes this callback. this is not some binding to a C web server. This is not like a thin binding to some C web server. The path that this request goes through to serve this buffer to the client goes through a lot of JavaScript. The HTTP server in Node is written in JavaScript. And it's a bit amazing that it can serve it that fast. And I think it goes to show you that V8 itself is quite good. But really, take this benchmark with a grain of salt. This is very special circumstances. I'm sure that I've got Nginx improperly configured. It's probably polling the file system. It's doing something in a way that is not optimal, okay? And of course, Nginx was using 4 megabytes of memory, and Node was at 60. However, that's fast. That is really, really fast. So the point is here that Node's fast. It's something that is in part due to the fact that V8 itself is just a marvelous virtual machine and very, very well done. But it's also because of all these callbacks that we've set up and the way that Node is forcing you to design your server. And this is going to be a bit philosophical. So a lot of websites have something like this. You request something from a database. You know, probably it's through some ORM layer, but you request something from a database, and you return the response. And then on the next line of code, you use that response. You abstract all the I/O that you're doing to the database in the form of a function that performs that I/O and returns the response. And the question is really, what is your software doing while it's querying this database? And sadly, in the year 2010, a lot of us are running Rails websites that simply do nothing. It shuts down while you query that database. It just sits there and waits for the response. Of course, this can be mitigated by using mini Rails processes and load balancing across them, and in that way you can handle more than one request per second. But the Rails process itself simply shuts down while it queries the database. And if you're doing some sort of active record thing where you do A, B, C, and D, and just query hit the database back and forth many times, that's a lot of go-around time. That's a lot of waiting for your web application. Yeah, I just throw in this slide to demonstrate something. The disk and the network are far, far away. They're in the distant, they're on the other side of the world. Inside the CPU, executing, adding numbers together, putting strings together, doing these sort of things, you can operate very quickly. But as soon as you have to go to disk, or if you have to go to the network, it's like getting in a plane and flying to Japan. It's a very, very different sort of time scale. Executing things in the CPU and touching memory as opposed to going out to the disk. So really, I mean, what we treat going out to the disk like this, accessing a database, as if it were just some function, you know? Oh, who cares what it's doing? I mean, it's just like any other function, right? It's just doing something. We also have like a function that adds two numbers together. Yeah, this one is one that accesses the disk. But something very different is happening here. The time scales are very, very grossly different. And the programmer, being just some web programmer, sits down and writes their website and has not seen this slide or doesn't care, just wants to get their project done. And at the end of the day has very, very slow websites. So it's really unacceptable in this year to wait for the database, to have a process sitting there waiting for millions of clock cycles while some disk is spinning somewhere when there's other people to serve. Like I said, you can mitigate this by load balancing across multiple processes, but this is a hack, right? These processes can handle a lot of connections, and you're not doing it properly. So, of course, better software can multitask, right? This is just Rails. There's much better software. You can have multiple threads, of course, so that you can make that database call, and you can shift to a different thread, and it can continue execution. But to make a long story short, this is not the optimal way to do things. Context switching isn't free, and these threads themselves take a lot of memory, comparatively. And so you'll see web servers like Apache that do this threading mechanism for each connection, taking a lot of memory when you scale up the connections. When you start, get into the hundreds or the thousands of connections, the memory just spikes up. Whereas Nginx, which packs a lot of connections into a single thread, has a very stable memory footprint and is quite fast. So it's very well known in the server community that you cannot use threads for each connection. So an alternative to that, to pack a lot of connections into a single thread, into a single process, is to structure your code with callbacks. So to query the database and then give a callback when it's complete. And in that way, it allows the program to make the call to the database, completely just keep going, like never stop. Make that call, serve the next request immediately. And whenever that responds in the distant future, millions of clock cycles in the future, go back and call that callback. So why is Node fast? It's fast because it uses this simple single process, single thread, single execution stack model with these callbacks, and it never ever, well, sometimes, but it never blocks on I/O. It never waits to make that call to the database. It does it like that. It goes immediately on. There's some things in Node that are clearly marked as synchronous that allow you to do things in a blocking way for file access. But that's just some convenience for certain situations. If it's not marked with sync, capital S, it's not blocking. You don't need to worry about it taking time. It as far as you're concerned, it takes 0 time to execute that, with respect to how long it takes for these I/O actions to actually happen. And JavaScript is really perfect for this. I didn't make this project because I love JavaScript. I kind of hate JavaScript. It's not like the ideal language, but it is very well suited to doing this style programming, where you make callbacks and you have just one single thread. So it has the necessary language features like anonymous functions and closures. And the browser API, how people experience it, is that one callback executes at a time. You don't have like 2 callbacks at the same time being executed. And it allows you to think about your website when you're programming for the web browser in a very good way. You don't have to lock your variables when you access them, because only one thing happens at a time. It all happens very quickly, but only once at a time, which is different than the typical server environment where there's lots of things happening at the same time. there's multiple CPUs that are actually executing the same code at the same time, and you try to access some memory, and so does the other one, and your whole thing breaks. So you have to be very careful about locking. The programming model for the web browser is extremely simple. Just one callback at a time. You get callbacks when people click it. And oddly enough, this is the optimal way to do things in terms of performance. We can have the argument later if coroutines are the right approach to get away from doing callbacks. I say no. And you can have a different opinion, and we can argue, and then I'll win. But no, coroutines are, we'll leave it for later. And most importantly is that every web browser programmer is already like prepared for this. You give this to somebody who's been programming servers on a Java stack for a long time, and they're like, whoa, why am I getting a callback here? This is super weird. I can't deal with this. It's spaghetti code. But you give it to a web browser programmer, and they're like, oh, great. It's like a button, right? Somebody makes a request. It's like when they click the button. It makes perfect sense. I mean, we've over the past 10 years, we've like trained a generation of programmers to do this evented style programming. Let's start using it for server side. So I'm very happy when people try out Node and they like write me an email and they say, wow, that was like super easy. Like I could intuitively understand how to write this TCP server, and I've never done that before. I think it's because of this browser programming model that they already understand and they can apply already to this server-side programming. So very quickly, we're getting more abstract now as we move on. The architecture of Node is basically three things. It's V8, which is the JavaScript interpreter by Google. It's an event loop abstraction, which is just, each different kernel has different ways of polling the operating system for, polling the kernel for new events, for finding out if a socket is readable or writable. And for example, on Linux, you use epoll, and on FreeBSD, you use KQ, and on broken Macintosh, you use select. And libev is a simple, very simple layer on top of that so that you don't have to write the code 3 times for each one. It just, when you're on Macintosh, it calls select. When you're on FreeBSD, it calls KQ. It's a simple abstraction over that. There's a thread pool, which is quite simple, just a bunch of threads sitting there, usually just one. And every time you make these file system calls are blocking. There's no way to get around it. Kernels largely do not implement the POSIX asynchronous I/O stuff. There's no system calls to manipulate the file system in a non-blocking way. You have to do it in a separate thread. So Node has a thread pool that is internal, is not exposed to the programmer, to execute these file system things. Like when we check the last modified time of EDC password, that was using the thread pool. So it's basically these 3 things with some bindings on top of that written in C. And then the large chunk of the source code is just JavaScript on top of these relatively thin bindings. So in JavaScript, you, the user, only ever interact with the main thread of execution. You only get callbacks, which are executed in the main thread. When you hit a signal, it is not asynchronous to the rest of the execution. It is marshaled back into the main thread. Okay, so everything is always in the main thread. However, the C layer does actually have multiple threads. You might complain that, I, as a JavaScript programmer, want to use that thread pool, damn it. You might complain that, hey, this is a big deficiency. Like, Node cannot utilize multiple threads. And I say, no, you're wrong. Everybody says threads should be used by experts only. Nobody really believes that, or they just think I'm an expert. But really, they're very complicated. They're difficult to use. It's difficult to get right. And I think it's appropriate to say, if you want to use multiple threads, sure, do it in C. That's a fine layer. For the JavaScript programmer, for the casual user, you don't want to dirty their environment with multiple threads. In fact, you can't even in V8 as it currently exists because you can't execute. V8 has no concept of threads. But that's fine with me. Even if we were doing this with SpiderMonkey, which did have multiple threads, I would not allow that to go into the JavaScript layer just because we want to preserve this very nice, simple view of the world. So quickly, a roadmap. So what are people using Node for now? Well, mostly nothing. I mean, it's very buggy, and the API changes a lot. But it is one of the few solutions. There's others, of course. But one of the few solutions for putting together a real-time sort of application for pulling down data from Twitter without hitting it with tons of requests, but just making a connection and having it stream data and proxying it somewhere else, like in our IRC room. Whenever somebody mentions Node, it gets proxied directly into the channel, and it happens instantaneously because the IRC bot that does that just has a connection open to Twitter, and it has a connection open to the IRC room. And so when somebody posts something in Twitter, it comes down and goes over here and takes approximately 300 milliseconds, which is the latency between Twitter plus the Twitter to the bot to the IRC server, I guess the latency to the client who then views it. It should be about 300 milliseconds. If it takes 2 seconds to get that Twitter update, you're doing it wrong, right? So you need this to do real-time sort of things. You need to be able to handle open connections, and open connections mean receiving events. So this is what people do now. They have their website, Rails, of course, proxied to load balance to hell because they suck, and you throw some Node thing on the side to handle your chat or your little tank game. But I think that Node will mature. I work very hard on it. I'm employed full-time to work on it these days. And there's a lot of interest in it. And I think that in the future, in the next couple months, the frameworks built on top of Node will mature. And people will start to be able to build entire websites with this, with a friendly API. Obviously, you can't give the API that I've just presented with this making a HTTP server and you get the request and response objects. You can't give this to the normal web developer, right? This is way too low level. But things can be built on top of this that make it simple to make simple responses. Query a database, get a callback, you put the data into a template. We're not there yet, for sure. But even then, you're probably going to want to put it behind an actual stable web server like Nginx, just because you don't know, you don't really want to have a process sitting on port 80 that we're kind of unsure about and that could crash at any moment. But I doubt load balancing will be necessary. So I think that in the next couple months, we'll see lots of websites that just kind of look like this, without the Rails component. And of course, in the future, I hope that Node will be stable and we will feel comfortable just setting it on port 80. This conference is about discussing the stack. Right now, we have a lot of things, a lot of layers, well, at least two. You have your load balancer, and you've got your application servers. You've got Nginx, you've got Rails, or you've got Apache, and you've got PHP. But largely, this setup is only necessary because these things are so slow. I think a single node process can handle the websites of all of you guys in this room. I mean, I'm quite certain that your limit on this is not your CPU or your memory, but rather your gigabit internet connection cannot handle the stuff that it's putting out. It won't need to be load balanced. Obviously, there's going to be websites like the Googles of the world that need to be scaled across multiple processes, and they're going to need load balancing. But for the vast majority of websites, i.e. all of them except Google and Facebook, we'll probably be able to live in one process on one computer. So I want to give one advertisement that I forgot to put in my slides before I answer questions. So there's a programming contest soon, which is like Rails Rumble that a couple of guys are putting on. And I think it's going to be really fun. So Rails Rumble is about building a website in 48 hours with Rails. This is about building a Node.js website in 48 hours. And where the Rails websites are typically to-do applications, to-do lists, or recipe books. I mean, Rails is really great at building CRUD applications, right? Connecting it to a database, putting up some stuff, modify that stuff. You know, this sort of application. Node websites, I think, have this feel of real-time stuff. And I think it will be interesting to see what sort of demos come out of this contest. Just, hey, let's throw together a real-time tank war website, or lots of sort of games. So this is 48 hours. I think it's the end of August, so you have a lot of time to think about it. But I encourage you to form a team. If you're in San Francisco, we're going to have we're actually going to have people like sleeping at our office and like camped out there and have it be really hacky and stuff.
So if you're in Paris, there will be something also. It's either will be here in the canteen if you can get it open all night, or it will be at the offices of a district.
Excellent. Okay. So yeah, this should be fun. And yeah, I look forward to, I love demos, right? I hate when people write web frameworks because it's so boring. Like let's make more demos. And I would show you a demo, but I think the screen's not so good. You can find some online. Questions? Yes?
So I have a message and a question. The message, the IRC room says hi. And the question is, how does it compare to Twisted in Python, if you know about it?
Right, so how does it compare to Twisted in Python? Yeah, it's a similar sort of setup. I did not invent this idea of an evented server bound to a dynamic language. There's Twisted, of course, from old times. There's Event Machine, which is very, very good. There's any event from Perl. Yes, it compares to them very well. It's nearly the same thing. I would encourage you to look at the examples of these other ones and just notice, not to say that you shouldn't use them. I think they're fine frameworks for things, but notice that JavaScript is very much built for this sort of thing. And these other languages, Python, Perl, Ruby, are not necessarily designed for this event loop sort of thing. You can do it fine, it works, but I would argue that it feels a bit more natural in JavaScript, just because it's the same syntax as the web browser, but Yeah, I'm not too sure how to put my finger on it, but it feels very natural. In terms of performance, they're all pretty much, in the large scope of things, they're on par.
I would just suggest that we close this thing. We'll have 10 minutes of a break. Then Richard Kreuter will do the MongoDB presentation. Afterwards, Ryan will do a breakout session somewhere. So people that want to ask geeky questions can get around him and kind of geek the hell. So thank you.
Thank you.